Good evening, students. So let me take up the semiconductor chapter, which is a theory one. It is completely a theory concepts. Semiconductor electronic devices. Okay. Now in this chapter, we are going to deal about the study of the semiconductors, how they are going to be used in electronic devices, how they are going to convert from AC to DC and all those things. Yeah. Before going to this, the classification of semiconductor and what is a semiconductor, you know the concepts of the band theory. Band theory of solids. Band theory of solids. You know that the solid consists of a many number of atoms. This consists of many number of atoms. These atoms contains two types of electron. One is called as a valence electron. The another one is called as the conduction electron. You know the electrons which are present in the outermost orbit. The electrons which are present in the outermost orbit, they are considered as what? The valence electron. The electrons which is going to constitute the current, they are considered as the conduction electron. So the electron which constitute current, they are considered as a conduction electron. The electrons which are present in the outermost orbit, they are considered as the valence electron. Whatever the energy is going to be formed by the valence electron, that band we call it as the valence band. The energy band formed by the valence electron is what we called as the valence band. And the energy band formed by the conduction electrons, that band we call it as a conduction band. So what is conduction band? Conduction band is the band formed due to the conduction electrons. The valence band is the energy band formed due to the valence electron. You know that valence electron is nothing but the electron which is present in the outermost orbit, and conduction electrons are the one which is going to be there due to the constitute of the current. Based on this band theory, based on this valence band and the conduction band, the semiconductors, the solids are classified into three types. The solids are classified into three types. These solids are classified into three types. One is called as the conductors. The second one is called as the semiconductor. The third one is what we called as the insulator. So conductors, semiconductors, and insulators. Then how do you define the conductors? Don't tell which allows the electron and which does not allow the electrons. That is over. But we are going to define these conductors in terms of this valence band and the conduction band. Based on the valence band and conduction band, we are going to explain how this band theory of solids are going to be classified. Yeah. In the case of a conductor band, if I say this is the valence band, the conduction band is going to be there, which is going to be overlapped with the valence band. There will be no energy gap. Energy gap is almost zero in the case of the conductors. So in the case of the conductor, the valence band and the conduction band are going to be overlapped here. So it is very easy to take the electron from valence band to the conduction band. Isn't it? So whatever the energy gap is there, that energy gap is almost about 0 electron volt, there will be no gap at all. And whatever the gap is there, that gap we call it as a forbidden energy gap. Whatever the gap is there between the valence band and the conduction band, this gap is what we called as the forbidden energy gap. Forbidden energy gap. So in the case of the valence band and the conduction band, there will be no gap between the two bands, hence the energy gap will be 0. That gap we are considered as the forbidden energy gap. But if you come to the semiconductors, please remember, if I say this is the valence band and there will be a little bit gap between the valence band and the conduction band, this almost is about close to 1 electron volt or less than that. If there is a small gap between the valence band and the conduction band, which is about 1 electron volt, then we consider as a semiconductor. Sir, we can take the electron from valence band to the conduction band? Yes, you can take, but you have to give the energy. By giving the energy only, you have to take the electron from valence band to the conduction band. In the case of the insulator, this will be a valence band and this will be a conduction band. This valence band and the conduction band are separated by a large gap. This large gap is about more than 3 electron volt, where the electron cannot take from valence band to the conduction band, because energy gap is small. So there will be no constitute of current in the case of insulator. Hence, we are going to say that insulators are the substances which does not allow the charges to flow through them, or where the current is not going to constitute in the case of the insulator. So this is how we are going to classify the conductors, semiconductors, and the insulators in the case of solids. This is the basic definition, students. In the objective, they may create the questions based on the theory oriented only. This chapter is completely theory, students. Yeah. And come to the main differences between conductors, semiconductors, and insulators. So differences between conductor, semiconductor, and insulators. First thing, please remember about the conductivity. You know that sigma represents conductivity, right? What is sigma represents? Conductivity. In the case of the conductor, the conductivity rise between 10 power 2 to 10 power 8. The value of the conductors varies from 10 power 2 to 10 power 8. For the case of the semiconductor, it is about 10 power minus 8. In the case of the insulator, in the case of insulator, it is 10 power minus 8. In the case of insulator, it is 10 power minus 8. In the case of the semiconductor, it is about 10 power minus 5 to 10 power 0. So this is how we are going to classify the semiconductors. So conductors, semiconductors, and the insulators. This is about the conductivity sigma. Please remember this. Now, can you tell me the current carriers? The current which is going to constitute is about what? In the case of a conductors, you know that the current is going to constitute because of what? Free electrons. In the case of an insulator, there will be no current constitute. So no discussion about the charge carriers in the case of the insulators. But please remember, in the case of the semiconductor, the current is going to constitute because of the free electrons, also because of the holes. Free electrons and the holes. These are the two charge carriers in the case of the semiconductors. So these are the charge carriers in the case of the conductors, semiconductors, and the insulator. You know the concept related to alpha. You know what is that alpha called? Alpha is a constant which you considered as temperature coefficient of resistance. But please remember, in the case of a conductors, this alpha value is going to be positive. In the case of the semiconductor, it is going to be negative. In the case of the insulator, it is nothing but 0. So temperature coefficient of resistance is positive for conductors, negative for semiconductors, and it is 0 for insulators. Please remember. And finally, you must know the concept of the electron density. You know, electron density means the number of electrons per unit volume. Number of electrons per unit volume is almost in the terms of 10 power 29 per meter cube. In unit cube, how many number of electrons are there in the case of a conductors? It is 10 power 29. And insulator, there will be no charge carriers only. And in the case of semiconductor, it will be ranges from 10 power 19 per meter cube to 10 power 16 per meter cube. Because please remember, the well-known semiconductors are germanium and silicon. If you are using a germanium, then the electron density will be 10 power 19 per meter cube, and for silicon, it is 10 power 16 per meter cube. This is the electron density in the case of the semiconductors. Clear? So these are the major differences between the conductors, semiconductors, and the insulators. They may create any objective questions related to this. Yeah. Come back to this. In the case of the semiconductor, now you have studied the concept of semiconductor. So semiconductor is the one whose conductivity lies between that of conductors and insulator. So semiconductors are the one whose conductivity lies between that of conductors and insulators. These semiconductors are going to be classified into two types actually. One is called as an intrinsic semiconductor. The another one is considered as the extrinsic semiconductor. How many types of semiconductor we have? Two types. One is called as an intrinsic semiconductor. The second one is called as the extrinsic semiconductor. The intrinsic semiconductor is the one which is going to conduct in its pure state. Extrinsic semiconductor is the one which is going to conduct in its impure state. Example for intrinsic semiconductor is a germanium or a silicon. Then we'll take the examples for extrinsic semiconductor later, but this extrinsic semiconductor is going to be classified into two types. One is called as a N-type semiconductor. The another one is called as the P-type semiconductor. So how many types of semiconductors we have? Two types. One is called as an intrinsic semiconductor. The second one is called as the extrinsic semiconductor. Intrinsic semiconductor is the one which is going to conduct in its pure state. Extrinsic semiconductor is the one which conduct in its impure state. And extrinsic is classified into two types. One is called N-type semiconductor. The second one is called as the P-type semiconductors. And one more thing, please remember, any type of semiconductor is an electrically neutral. Even if they are asking N-type semiconductor, even N-type semiconductor is also electrically neutral. P-type semiconductor is also electrically neutral, because basically the semiconductors are made up of with atoms, which atoms are electrically neutral, you know that. So any semiconductors are not a charged one. Don't be under the impression that N-type semiconductor means negative type. No. All N-type semiconductor and P-type semiconductors are electrically neutral. Clear? Yes. Now you know that this germanium or a silicon contains the 4 electrons in the outermost orbit. So how many valence electrons are there in the silicon or a germanium? 4 electrons. So if I consider a germaniums, there will be 4 electrons. All germanium will form a covalent bond. If I send the energy to the germanium, this covalent bond breaks, 1 electron becomes free. 1 electron becomes free, there will be a vacant. This electron we call it as a free electron, and this vacant space is what we call as the holes. So holes is a positive charge carrier and free electron is a negative charge carrier. Because of this reason only, this electron and this holes becomes the 2 types of charge carriers. So please remember how many types of charge carriers we have. 2 types of charge carriers we have. One is called as the free electrons, and in the case of the positive charge carrier, it is a holes. So if I say Ne is the number of electron concentration and NH represents the number of hole concentration. If I recombine all these things, this will be N square. So number of electron concentration into number of holes concentration is nothing but N squared, where N is the number of electron hole combination. This is what we considered as the mass action law. So mass action law. So number of electrons into number of holes is equal to number of hole electron concentration squared together. They maybe create the problem based on this simple formula, students. By giving electron concentration and hole concentration, they will ask you to find N. So this is one basic simple formula to find out the electron concentration or a holes concentration or electron hole pair concentration. Now, suppose if you are going to add some impurities, which we call it as a dopant. If you add any dopant to the intrinsic semiconductor, it becomes a extrinsic semiconductor. So in order to get an extrinsic semiconductor, we have to add the dopants to the intrinsic semiconductor. By adding dopants to the intrinsic semiconductor, we are going to get the extrinsic semiconductor. To get a N-type semiconductor, you have to dope with a pentavalent element. You have to dope with a pentavalent element. In the pentavalent element, we are going to dope with like phosphorus, arsenic, bismuth, and antimony. All this contains 5 electrons. For the case of the P-type, we have to dope with a trivalent elements where it contains with boron, aluminium, indium, gallium like that. Indium and gallium like that. This all contains a trivalent which contains only the 3 electrons. So in the case of the N-type, please remember electron concentration is more compared to the hole concentration. But in the case of a P-type, hole concentration is more compared to the electron concentration. Because of more electron, only it is considered as a N-type semiconductor. Because of more holes, it is considered as a P-type semiconductors. So this is how we are going to analyze the concepts like the extrinsic and intrinsic semiconductor and N-type and P-type semiconductors. So these are the basic classification of the solids based on band theory and the further classification of the semiconductors. So please, you have to remember this formula, basic formula related to the electron and hole concentration, that is Ne into NH is equal to N squared. Got it? Yeah. Now, come to the next very important concept, students. That is called the PN junction diode. PN junction diode. PN junction diode. Yeah. Now, let me consider a pure semiconductor. Let me consider a pure semiconductor. In this pure semiconductor, I will make half of that. For the first half of that, I'm going to dope with p-type. Second half, I'm going to dope with n-type. N-type means it contains what? Electrons. P-type means it contains what? Holes. Done. What will happen? This hole is going to recombine with this electron. These two are going to recombine. After recombining, it forms a junction. But this hole and this electron will not recombine. This will not recombine. Why it will not recombine? Because there is a region here. It cannot cross this region. This region is what we called as the depletion region. Depletion region. Because of this depletion region, these holes and the electrons will not recombine. These holes and free electrons will not recombine. So whatever the junction has formed here, that PN junction, this is what we call as the PN junction diode. So if I consider a PN junction diode means this region is what we called as the depletion region. This is called P-type and this is called the N-type. And the thickness of this depletion region is about 10 power minus 6 meter micron. What is the thickness of the depletion region? The thickness of the depletion region is about 10 power minus 6 meter, that is micron. Micron. Suppose if the diode is not connected to any external source, then it is said to be unbiased. When the diode is said to be unbiased, the diode is said to be unbiased. The diode is said to be unbiased if the diode is not connected to an external source. Here the diode is not connected to external source. If the diode is not connected to an external source, then the diode is said to be unbiased. If the diode is connected to an external source, then it is said to be a biased. Under this biased, we have two types. One is called as the forward bias. The second one is called as the reverse bias. In the case of the forward bias, this is P-type, this is N-type. If P-type is connected to positive terminal and N-type is connected to negative terminal, then this is said to be a forward bias. When the diode is said to be forward bias, if P-type is connected to positive terminal, N-type is connected to negative terminal, then it is said to be a forward bias. In this forward bias, the depletion region will decreases. Because of the depletion region, the holes and electrons will recombine. Because of this recombination of holes and electrons, the current is going to constitute. If it constitute current, you know that if there is a flow of current, there will be no resistance. So it offers low resistance. In forward bias, it offers low resistance. So in the case of the forward bias, P-type is connected to positive terminal, N-type is connected to negative terminal, and there is a recombination of holes and free electrons. This is what we considered as the forward bias. In the forward bias, there will be a constitute of current and it offers low resistance. In the case of the reverse bias, this is depletion region, this is P-type, this is N-type. P-type is connected to negative terminal, N-type is connected to positive terminal, then the diode is said to be reverse bias. If P-type is connected to negative terminal and N-type is connected to positive terminal, then it is said to be a reverse biased. In this reverse bias, the depletion region will increases because these holes which are there in the P-type, it will move towards the negative terminal. The electrons which are there in the N-type, it will move towards the positive terminal. Because of this region, because of this case, the depletion region width will increases. Because of that more increase in the depletion region, the current values start decreasing. So it will not constitute the current. Why the current is not going to constitute? Because the depletion region width increases. Because of that more depletion region, the holes and electrons cannot recombine. Because of that, it will not constitute the current. Once if it not constitute the current, the resistance will be more. The resistance will be more. So please remember, which bias will offer high resistance? Reverse bias. Which bias will offer low resistance? Forward bias. Now, let me analyze the current voltage characteristics. Current voltage characteristics of the diode. Suppose if I consider the voltage along the x-axis and the current along the y-axis. For forward bias, if I increase the voltage slowly, for up to certain voltage, the current will be almost zero. Then after it starts slowly increases and gradually it becomes increases. Sir, why up to certain voltage the current is zero? Because up to that voltage the current is not getting because of the depletion region presence. Because of the presence of the depletion region, we are not getting any constitute of current even if you are giving the voltage. For one particular voltage, the depletion region thickness will completely become zero. Then the current gradually increases. At which particular voltage, the current becomes gradually more. This voltage, we call it as a cut-in voltage. So what is cut-in voltage? Cut-in voltage is the one which is going to be the voltage at which the current become gradually more. So if the voltage is one particular voltage at which the current becomes maximum, that voltage we call it as a cut-in voltage. Please remember this. And please remember, for germanium, it is 0.3 volt. If it is a germanium, For germanium, the cut-in voltage is 0.3 volt, and for silicon, the cut-in voltage is 0.7 volt. For germanium, cut-in voltage is 0.3 volt. For silicon, the cut-in voltage is 0.7 volt. You have to remember this. Please be very careful. If you plot the graph for the reverse bias, it slowly increases and it becomes breakdown. At one particular point, it will break down. This voltage at the semiconductors will break down is what we called as the breakdown voltage. For this, if you calculate the slope, for this, you know the slope is nothing but I by V, which is nothing but 1 by R. So the slope of this IV graph represents the reciprocal of resistance, which is nothing but the conductance. Reciprocal of the resistance is nothing but the conductance. So slope represents the reciprocal of resistance, and that reciprocal of resistance is called the conductance. So this is the characteristics of the current and the voltage in the case of the diode. And please remember, the symbol representation of the diode is like this. The symbolic representation of the diode is this. This is called a P-type. This is called N-type. This terminal we call it as an anode, and this terminal we call it as a cathode. This is the symbolic representation of the diode. What is the main use of this diode? Main use of this diode is going to be used in the case of a rectifier. Mainly this diode is going to be used as what? The rectifier. Rectifier is going to be classified into two types, where it is going to convert AC into DC. Actually, rectifier converts alternating current to the direct current. Alternating current is the one which changes its direction for every of a cycle like this. Direct current will not change the direction, it will be remain the same. If 50% of AC is converted into DC, then this is called as the off wave rectifier. This is called off wave rectifier. Suppose if 100% of AC is converted into DC, then it is considered as full wave rectifier. So if 50% of AC is converted into DC, then it is called an off wave rectifier. If it is 100% of AC is converted into DC, then it is called the full wave rectifier. So in the case of the off wave rectifier, only one diode we are using. If I give the input like AC, output will be only for off of the cycle. For this we'll get output. For this cycle we won't get the output. For this we'll get output. For this we'll not get the output. So only 50% of AC is converting into DC in the case of a off wave rectifier. Only we are going to use only one diode. The circuit will be like this. This is a variable transformer. This is a variable transformer. This is the diode. This is the load resistance, RL. This is connected to the output. Here we are applying an AC source. For first off cycle, this will become forward bias, there will be a flow of current. For next off cycle, this diode will become negative. There will be no constitute of current. So please remember that. And if you find out the efficiency of this off-wave rectifier, almost this efficiency of the off-wave rectifier will be 40.6%. Efficiency will be 40.6%. Exactly one, we won't get 50%. So please remember, the efficiency will be almost close to 40.6%. In the case of full wave rectifier, in the case of full wave rectifier, we are using the concept of the two diodes, where if I give the input like this, output for both the cycles, we are getting output. So 100% of AC is converting into DC. But for first off cycle, we will get for diode D1. Second off is conducting because of the second diode D2. Third cycle will get because of D1. Fourth cycle is because of D2. So if I say this is the transformer, there will be two diodes. This is D1 and this is D2. For this, we are going with center tap transformer. Here we are going to take the output. For first stop cycle, D1 will conduct. For next stop cycle, the D2 will conduct. Anyway, this is connected to the AC source. So in this way, for the first half of the cycle, if the diode D1 is conducting, for the next half cycle, D2 is going to conduct. In this way, both the cycles will constitute the current from AC to DC. Please remember, the efficiency of this is going to be close to 81.2%. Double that. So for off-wave rectifier, it is 40.6. For full wave rectifier, it is about 81.2%. So this is how we are going to use the concept of the conversion of AC to DC. Actually, there will be a one special type of diode, because you know that the normal diode will not work in reverse bias. So the new diode was introduced, which going to works only in the reverse bias. That special type of diode is what we called as the Zener diode. So Zener diode is specially designed by heavily doping. By heavily doping, the Zener diode is going to be constructed. And the Zener diode, which is heavily doped, is going to be used to work only in the special case of reverse bias. So Zener diode works in reverse bias. And this is the symbol of the Zener diode. This is the symbol of the Zener diode. For what purpose the Zener diode is going to be work? Mainly the Zener diode is going to work for voltage regulator. What's the main use of the Zener diode? Zener diode is mainly used for voltage regulator. You know what is voltage regulator? Voltage regulator is the one for any changes in the input. For any changes in AC input, constant output will be there. For whatever the changes are there taking place in input, even if you increase or decrease the input, the output is going to be the remain same. Even if you increase or decrease the input, output voltage is always going to be a constant. Such a device is what we called as the voltage regulator. This voltage regulator is going to be mainly used by Zener diodes. So what is the main use of the Zener diode means? It is mainly used for voltage regulator. It is mainly used for voltage regulator. Got it? So these are the main uses of the diodes. Actually, there are other design, specially types of diodes are going to be devised, which we call it as an optoelectronic device. So these are mainly a diodes only, but basically it is used to convert the energy from one form to another form. They are considered as a optoelectronic devices. Basically, we have three types of optoelectronic devices. One is called as a photodiode. The second one is called as the light emitting diode. The third one is called as the solar cell. So these are the three types of optoelectronic devices. One is photodiode. The second one is light emitting diode. The third one is called as the solar cell. Photodiode is the one which converts the electrical light energy into electrical energy, which is converting light energy into electrical energy. And this photodiode mainly works in reverse bias. But this light emitting diode will convert electrical energy into light energy. Electrical energy is converting into a light energy in the case of the light emitting diode. And this works in the case of forward bias. But the solar cell, this solar cell is going to generate, this solar cell will generate the EMF when solar radiation is incident on it. When solar radiation is incident, it is going to generate the EMF. That is what we call as the solar cell. Solar cell is no biasing. There will be no biasing in the case of the solar cell. Got it? Yeah. The last concept, you have studied about the concept of the logic gates. You know that in the case of the logic gates, we are going to analyze how the output is going to get for the different inputs. How the output vary with respect to different inputs. What are the different values of the inputs you are giving? For the different values of the inputs, how the output is going to change, that we are going to analyze in the case of the logic gates. In the logic gates, we have two digits. Usually it is going to be denoted with either 0 or 1. And there are different types of logic gates. One is called as the AND gate. This is the symbol for the AND gate. If A is the input, B is the input, output will be A into B. If you go to the second gate, it is OR gate. Symbol of OR gate will be this. Input is A, this input is B. Output will be A plus B. The third one is the NOT gate. Input will be 1. Output will be inverter of that. Because of this inverter only, this NOT gate is also called as an inverter gate, which is also considered as a universal gate. Because by using the NOT gate, we can combine or we can get a AND gate and the OR gates. There are two more additional gate students. That is called the NAND gate. It is the combination of AND gate and the NOT gate. So if I give the two inputs like this, A and B, and this NOT gate is going to connect, output will be A into B bar. And the special case, that is also a NOR gate. For the NOR gate, it is the combination of OR gate and the NOT gate. Combination of NOT gate and the OR gate, that is called the NOR gate. Symbolic will be A plus B bar. So these are the different 5 types of the gates, students. You have to remember, this is the first gate, OR gate is the second one, NOT gate is the third one, NAND is the fourth one, NOR is the fifth gate. So this are the logic gates. So this is the concept, a brief synopsis on semiconductor electronic devices, students. And as I said, it is completely a theory-based concept. There will be no problems on this chapter. Maybe the questions which you are going to get in the competitive level, it will be basically a theory-based question only. If they are creating a question means numerical type question means they maybe create the problems to calculate the forward resistance or to calculate the electron hole concentration, or they may ask you to write the truth table for logic gates. If you can solve all those things if you know the formulas of the logic gates, forward bias resistance, by using the concept of Ohm's law itself. So this is the brief synopsis on semiconductors. So in the next class, I'm going to take up the questions on these semiconductors. Even the questions is quite simple from this chapter, students. So I'll take up the question in the next session, students. Thank you.